Okay, now, as we have learned so far, the concepts of the Monte Carlo estimation, and also, more importantly, we talked about the importance sampling. Now we just want to simulate some data to visualize the concepts of the importance weights, and more importantly, to check if the proposal, I should say, distribution that we have has a finite, I should say, the variance, because that's going to be a key thing in the thing that we have discussed so far. But before we start, I just want to just show that to you before we just go to the R stars. I just going to just remind you of the things that we did. We said that in the concepts of the importance sampling, the thing that we did was very important. We said that if you are just looking into the integral of, let's say, the function which is going to be f of x, which we are looking with the distribution of the p of x, we said that we can just come here with the proposal distribution of the q of the x, d of x. Then we said that we can just have this concept as to be the average of the sigma. Now, before we were sampling from the p, now we are sampling from the q, which is going to be the f of xi, p of xi, which they are all being evaluated from the samples now, which is drawn from now the q distribution, qxi, and as you can see, I starts from 1, goes to the n. And more importantly, the thing that we talked before was that this one is going to be, it's getting close, it converges to the true value of this integral if we take that the number of the samples and the trials that it take to go to the infinity, and we could think of it as the limit of this one goes to the infinity. And that was the thing that we discussed. And also, if you remember, the thing that we did, it was had very significant implications for our analysis, was that we talked about this expression there. We said that we called the pxi over qxi. We call that as the weight xi, which, if you remember that, we just denoted them as essentially the importance weight and that's why we just call them with the W. We said that one of the significant and one of the most important thing about, I should say, the importance weights is that they have to just converge. You cannot have the variance which they have essentially to be infinite. The variance which they have, I mean, in terms of the importance weights that we have between the true distribution and the proposal distribution, I should say it should be not infinite. It should be a finite variance. And now that's the thing we just want to just go to the R to double check that at what do we mean by this and how we can have some kind of diagnostics in terms of, I should say, to see if the variance that we have with the weights in our importance sampling is going to be, I should say, finite. In order to do that, before just we do some kind of simulations, we need to install a package. The package, you see that it is called DIAGIS, Diagis, and you know how to install the package. You just command it with the install.packages, and when the package is installed, you have to just call it by the library command, which you say that the library Diagis, and you can say that, okay, if at the end, in case if you just want to make sure that the package is being installed, you can just go to the packages tab inside the global environment. At the right side of your, I should say, RStudio, you see that the package, Diagis, has a tick, which shows that that's a diagnostic plot, and multivariate summary statistics of weighted samples from the importance sampling. And that has a tick, which it means that the package and its functionality is now ready to be used in our analysis then. In order to start, I'm just going to just take a true sample of, let's say, for example, I'm just going to use the gamma sample, gamma distribution. And I'm going to start with that one to just talk about gamma distribution. I hope that if you have not yet just worked with the gamma distribution, it's very easy. Just please Google that on as a gamma distribution. And normally the best informative, I should say, description of the gamma distribution, that's the thing which comes with the Wikipedia. And also there is infinite number of the literature that you can just go through and search for the gamma distribution. But we do not have that much detailed knowledge of the gamma distribution. We need some kind of basic definition of the gamma distribution, that we need two parameters, which is going to be about the shape and the scale parameters. We call them alpha and beta in order to define a gamma distribution. It's essentially, if I just want to just go back to the whiteboard that we had, for example, with the normal distribution, we have seen that we have, for example, two parameters, which is going to be, for example, the mean and the dispersion. And also for the gamma distribution, as we're just going to see, we need two parameters, alpha and beta. Alpha defines the shape and beta defines the scale of your distribution. I think knowledge of these two things, as brief as this is going to be essential for us now that we just want to just go ahead to just do some simulations for the importance weights and importance sampling with the gamma distribution. I'm just going to define the x, and I'm just going to store my distribution. I'm just going to go ahead with the command R gamma. I'm just going to define, for example, the number of the observation, which is going to define my later the distribution. In terms of the n, the number of the observation, I can just come ahead with any numbers you want. For example, you can just go ahead with 20,000. I'm just going to have a huge number of the observation in order to just use, I should say, somehow the rule of the large numbers. And also, in terms of, for example, the shape and the scale, I'm just going to go ahead with the 1, and also, for example, I can just go ahead with the 0 point, let's say, 7. I'm just going to now execute this line, and you will see that this the R gamma, it is stored within, I should say, the object, which is going to be the x. And also, the other thing which we want to do is we just want to find the weights. Imagine that the x, I'm just going to go ahead to define, I should say, for example, my true distribution. For my true distribution, I'm just going to define it as the P of x, which I'm just going to store that, which is going to be based on the distribution, which is going to be the distribution of the gamma. We call that B gamma. Now I have this one. For the x, the number of the observation, I'm just going to pick up the things which I have created here. I'm just going to go ahead with the x. And now, for the shape parameter, I'm just going to go ahead with any numbers you want. You can just go with the 2, for example, and you can just go with the scale, just go to the 1. And now, I think that's all that we needed in order to define a gamma distribution in R, which we define the number of the observation, which is going to just comes inside the distribution, and also a parameter for the shape, which we just randomly choose it, anything you want, which we just take it as a positive 2, and also for the scale, we just take it 1. And now it's going to be, we execute that line by pressing Control Enter, and we have the P of the x, which is going to be a true distribution, it's going to be defined as the P. However, on the next line, we are just going to go ahead with the proposal, I should say, distribution, to define the proposal distribution, and we call that the Q of the x. And that's the thing which we have normally done that. I'm just going to store the gamma distribution, which is going to be D gamma. And now I'm just going to come ahead with the same thing. I'm just going to pick up the same number of the observations which I had. And in terms of, I should say, its scale and the shape, I'm just going to go as with 1. And let's say, for example, a very easy number. For example, a scale, which is going to be 0.5. I'm just going to execute the line. And I have, I should say, my proposal, I should say, distribution has been stored in the object, which is going to be Q. The other thing which we do, as you have seen that on the whiteboard as we did, in order to find the weights, we have to just divide a ratio. To define the ratio, as you can see here, with respect to as you will see it here, with respect to the true distribution, which is going to be divided by the proposal distribution. And that's how we define, I should say, the weight distribution. I get the weight samples. We're just going to call it as W of X. You can call it anything you want, but we're just going to call it with the W of the X. And I'm just going to simply define by the P of X divided by the Q of the X. And now I'm just going to execute the line by pressing Ctrl Enter, and you see that the code is being executed now. Now, we have the W of the X. Oh, I had to just have a capital W for my weights. And you see that we have, I should say, a number of the weights that it has been created here. Now, however, in order to visualize it, I'm just going to simply just use a command W plot of, let's say, the W. And you should expect to see the plot which is being generated in just a couple of seconds. Then I'm just going to zoom it, and you see that this one has been created all over, I should say, the pictures which we have. We have the number of the observation. This is maximum to 20,000 observation, and you see that these dots represents these distributions then. And it represents, I should say, the weights which I have. However, based on the thing that we have just taken here, we can just, from the package, we can just come here with some, I should say, from the digest the package, we can just get some, for example, definition of, for example, the weight mean. You can just come here with the W, X. You can see that, for example, the weight which they have, for example, it's going to be a capital one. Weight mean. Give me a second. That's going to be this one. We just put it as a weight with the capital. Just go ahead with the X. Argument W is missing. Let's go ahead to just go with the help menu. Okay, in order to do that, we had to just put the X. I had to define also the X there, then before just go for the mean. That's the thing which I just forgot to include, and that's sometimes very helpful to see the help before you just go ahead. We just put the commands there. You see that the weights which you had, essentially they have, I should say, the mean of the samples weights we have is going to be 1.67. These ones is not going to be as important as some diagnostics that we are just going to do right now, which is going to be the weight, I should say, weight plot. And that's the thing which we are just going to do. And simply we just go ahead with the functions which we have with the weight X, and we execute the line, and we expect to see at least 4 plots that it's going to be a kind of a diagnostic implications for the samples that we have. And now the plot is generated, and now I'm just going to spend a couple of minutes before we stop these tutorials to talk about the weights. And more importantly, because the thing that we talked about the weights, about the variance, that's going to be the thing that we just want to talk about that. I'm just going to go ahead to interpret these plots, which all of them is taken from the weights that we have taken as an importance weights. See what do they mean. I just start from the first plot, which I have the weight with respect to the index which they have. The index is going to be, let's say, 20,000 weights which I have, because I had 20,000 observation, and they're just going to be the index line on the horizontal axis on my first plot. And you see the weights, which is, I should say, you see that they are scattered. You have 100 largest weights. You see that these weights are randomly on the plane. And that's a good thing. It shows that our analysis is not dominated by only one single weight. I'm just going to go back on the next tutorial to just go ahead with an example which shows that how the sampling which you have done and how the, I should say, the proposal, I should say, distribution that you have done can result in a very disastrous, I should say, weights. But at this point, we see that the best benchmark to analyze and to have a diagnostic tool for the importance which that you have in your analysis is that when you have, for example, based on the number of the observations that you have and you have 100 largest weights, you have the weights are randomly scattered on the plane, and you do not see just, for example, an ordered, for example, line. For example, all the points are just geared towards only one weight, which is going to be a disastrous thing. We do not expect that thing. We expect to see all the weights around the plane. We do not expect to see, for example, all these 100 largest weights to be clustered around only one single weight, for example, 1.4. That's the thing which we have to avoid. And also, on the second one, which is, you see that the index, which is going to be, again, 20,000 index we have, because we have 20,000 weights, because we have 20,000 predefined, I should say, observation, and you see that the value of the weights, you see that the weights is going to start from the 0 and increases gradually, and you see that it converges to the maximum weight of 1.5. You can expect that the largest weights that you have, I should say, in your analysis, is going to be somewhere between 0, which is going to be very reasonable, go all the way to the maximum of 1.5. That's going to be the largest weight in your important sampling which you have from your distribution. However, we are going to go to this plot, which is going to be the most important diagnostic tools from your weights, and that's going to be the concepts, I should say, of the variance of your analysis. For the variance, you see that, again, on the horizontal axis, we have from 0 to 20,000, because as I said before, we had 20,000 observations as a predefined value in my, I should say, analysis. And also we have the variance here on the y-axis. You see that the variance starts to just increase from 0. And now you see that as the number of the observation increases and the index increases, you see that the variance, it seems that it comes to some kind of stability. It converges to a number, as it seems to be, for example, converges asymptotically to a number which it can be besides is 0.2. And that's a good thing, which it shows that the variance of the distribution weights, of the distribution samples, and of the sampling weights and the important samples is not infinite, and we see a kind of stability of the variance of my weights which I have in my problem, which is the best and the most important thing as a diagnostic tool when you just work with the importance sampling and the importance weights, to show that your weights, the variance of your weights, this is not indefinite. This is a defined, and I should say a finite variance of your samples. And now, for this plot, it's not kind of that kind of a thing that we can just use that with the kind of a thing that we need for analysis. But now, before we just finish these tutorials, I'm just going to go ahead to just simulate a kind of a plot, which we will see that it just not produces these characteristics of a good importance sampling weights. I'm just going to go back to the R, and I'm just going to make some changes with the, let's say, for example, the X. Let's keep the X to be the verb it is. I'm just going to go to change the proposal to, instead, I just put, for example, the scale to be 3. I have everything as this before, and I just go to the weights, and I just go to the plots. Let's see what do I get for the plots of my diagnostic importance weights. It takes a couple of seconds before we have the weight plot generated, and now there we have. For example, you will see that only by changing the proposal weights distribution which I have, by changing the scale parameter from from the thing which I had before to 3, increasing the scale, let's see what do we have on those diagnostic plots on this scheme. Okay, now look at that. I'm just going to start from the first diagnostic tools which we have, which is going to be, I should say, the 100 largest weights which I have up there. You see that the index is going